Welcome to the first of two videos about the most common types of distortion artifacts in digital audio recordings. These videos presume that you're already familiar with basic principles of digital audio such as sampling rate, Nyquist frequency, and bit depth. If you're not familiar with these concepts, we recommend that you watch our earlier video introducing the basics of digital audio before watching this one. This series of videos was produced with a particular focus on the needs and interests of biologists who want to work with digital audio recordings of animal sounds. However, these videos mostly cover general principles that are not in any way specific to recordings of animal sounds. If you're new to digital audio and your interests are in other applications, such as recording music or speech, you might find these useful as well. What do we mean by artifacts? Artifacts are specific types of distortions in a recording that result from errors either in the original recording process or in later manipulation of the digital recording. If you don't recognize these artifacts, you can end up with erroneous descriptions or measurements of the sounds. So it's important that you understand how to recognize these artifacts and what they mean for what you can and cannot legitimately do with a recording. We'll be covering the two most common types of distortion artifact in this and the next video. In this video, we'll be talking about the most common type of distortion, namely amplitude clipping, or simply clipping for short. Clipping is the term that's used for a type of distortion that occurs when high amplitude portions of a sound exceed the maximum that can be accurately represented by the recording system or by the digital storage format. Clipping is not uncommon in field recordings. If you work extensively with field recordings, you're quite likely to sooner or later end up working with some recordings that are clipped. In the next video, we'll talk about a less common type of artifact called aliasing. Before we jump into considering what clipping is, how it occurs, and how to recognize it, it's useful to review the specifics of the digital audio recording chain that were introduced in the previous video. Recall that the digital recording chain is a three-step process. In the first step, a microphone converts a continuous sound pressure wave in the atmosphere, in water, or in some other medium into a continuous time-varying voltage signal. In the second step, the small voltage signal from the microphone is amplified by a device called a preamplifier, or preamp, which is usually built into the recorder. The output of the preamplifier is an electrical waveform that has a similar shape to the waveform output by the microphone but has a larger amplitude. And finally, in the last stage, a device called an analog-to-digital converter, or ADC, or digitizer, samples this continuous voltage waveform many times per second, creating as output a series of sample values over time. The individual sample values are proportional to the sound pressure that was originally detected by the microphone, measured or sampled at successive points in time. The number of times per second that the digitizer samples the electrical waveform is called the sampling rate. Common sampling rates for sounds that humans can hear are 44.1 thousand, 48,000, or 96,000 hertz, or samples per second. Clipping occurs when the input to one or more of those three components, either the microphone, the preamp, or the digitizer, exceeds the maximum value that that device can accurately represent in its output. When this happens, the output of the device is said to be clipped at its maximum possible value. As a metaphor for this, consider an analog speedometer in a car. The maximum speed that this speedometer can represent is 190 kilometers per hour. But supposing we're actually driving at 200 kilometers per hour. The speedometer is still going to read 190 because it doesn't go up as high as 200. It's not going to give us an accurate reading of the speed because we've exceeded its maximum possible output value. Let's talk first about the most common form of clipping that occurs in digital audio recordings, which is what's called digital clipping. Digital clipping is what happens when the electrical waveform that the digitizer sees as input exceeds the maximum amplitude that the digitizer can represent accurately. In this illustration, the smoothly varying blue curve represents the time-varying sound pressure of a very simple sound, namely a pure tone, which looks like a sine or cosine wave. This is what the voltage waveform coming out of the microphone and the preamplifier would look like. It's the same shape as the pressure waveform of the actual sound wave in the air as received by the microphone. Here, the red dots represent the individual sample values that are output by the digitizer at regularly spaced intervals in time as determined by the sample rate. Depending on the bit depth or sample size of the digitizer, which is typically either 16 bits or 24 bits, there is a specific minimum sample value and maximum sample value that the digitizer can produce as output. In the case shown here, the analog waveform never goes below the minimum sample value or above the maximum sample value. So in this case, we're able to produce an accurate digital representation of the original analog sound pressure waveform, and we have no clipping. Let's look now at a case where the amplitude of the analog waveform coming into the digitizer exceeds this range of values that can be represented given the current bit depth of 16 or 24 bits. Notice that the smoothly varying blue curve at the top goes above the maximum possible sample value and goes below the minimum value at the bottom. As a result, the digitizer cannot produce output samples that accurately represent the shape of the waveform. Instead, it produces the maximum or minimum value that it is capable of given the bit depth. And so we get these inaccuracies in following the shape of the waveform at the minimum and maximum values, and this is what causes clipping. So, digital clipping occurs when the amplitude of the input signal to the digitizer exceeds the digitizer's range of acceptable values. In that case, we say that the waveform is clipped. Let's take a look now at what a normal unclipped signal and a clipped version of the same signal look like in Raven, and also what they sound like. Here we see a Raven window showing two panels. The top panel shows the waveform of the signal. The vertical axis represents the individual sample values. The bottom panel is a spectrogram. This is a pure tone at 440 Hz, or in musical terms, the A above middle C. And you can see in the spectrogram that there's just a solid horizontal line at 440 Hz. Let's listen to that. In the waveform panel on the top, notice that there is a white background behind the blue waveform. And above and below that white area, there's a gray background. The boundary between the white and gray background represent the limits of the sample size given the bit depth of the file, which is 16 bits. Those are the minimum and maximum values that the digitizer could have produced when recording this sound. Let's look at what happens to the same sound if it's recorded with greater amplification, or if it's amplified after recording beyond the limits of what the 16-bit sample size can represent accurately. Here on the right, we see a waveform of the same sound, but it's been amplified, so that the tops and bottoms of the waveform exceed those limits of the 16-bit sample size. Notice that what were smoothly varying tops and bottoms of this sine wave are now flattened because the extreme ends of the waveform can't be represented. They would require sample values beyond the capability of the digitizer to represent. So you can tell by looking at the flattened top and bottom of this waveform that it's clipped. Let's listen to what this sounds like. It's similar. It has the same pitch as the previous version, but it has a sort of slightly buzzy or dissonant quality to it, not as pure sounding as the original 440 Hz tone. If we look at the spectrogram, we'll notice that the original horizontal line, or spectral component, at 440 Hz is still there. But in addition, there's a series of lines above that at multiples of 440 Hz. So there's a faint line at 2 times 440, or 880 Hz, a more prominent line at 3 times 440, or 1320 Hz, and so on for integer multiples of 440. These are called harmonics of the sound. And they're actually what we would call spurious harmonics. In other words, they're not real. They're artifacts. They weren't really in the original sound. The original sound had no energy at those higher frequencies. But because the waveform got clipped in the digital recording process, that gives rise to this additional energy in the resulting digital recording that wasn't really there in the original signal. This is an illustration of what happens when we have digital clipping. Although digital clipping is the most commonly encountered type of clipping, clipping can also occur if the mic or preamp is maxed out, even if the digitizer isn't. Clipping at the microphone or preamp is called analog clipping. Here's an example of analog clipping in a recording of a South American frog. Let's listen to this. In order to see and hear better what's going on in this recording, I'm now going to zoom in on just the first of these 3 notes from this little frog. Now I'm going to play the recording at 1/4 speed, repeated 3 times. Let's listen carefully. The entire call is around 180 milliseconds long. Throughout that time, there's a short stack of harmonics, all below about 6,000 or 7,000 hertz. But between about 220 and about 270 milliseconds, a tall stack of additional harmonics appears. If we look at the waveform, we see that during the periods when those extra harmonics appear, the top of the waveform is flattened. That's because either the microphone or the preamp was clipped. It reached the maximum amplitude that it could produce, resulting in flattened waveforms during these periods, rather than smoothly varying waveform envelopes as we typically see. And whenever the waveform is flattened by clipping like this, these extra harmonics appear. These extra harmonics are actually spurious harmonics, meaning that they really shouldn't be there. The animal never made those sounds, and they're merely an artifact of the distorted recording. When we listen to the recording slowed down to 1/4 speed, we can hear that when these spurious harmonics appear, the sound becomes kind of buzzy or distorted sounding as a result of the clipping. Let's listen to that again. We can tell that this recording is not digitally clipped because the tops and bottoms of the waveform don't reach the edges of the range of possible sample values. Remember that in Raven, those limits are indicated by a gray background that's not visible here. So how can you recognize clipping in a recording? It's important to know whether or not the recordings that you're working with are clipped. Keep in mind that clipping can only be diagnosed by close examination of the waveform. In the case of digital clipping, it's easy to tell when a waveform is clipped in Raven Pro because Raven shows you the range of valid sample values by a white background to the waveform. The limits of that range are indicated by the gray background above and below the waveform. If the blue waveform hits that edge, either at the top or the bottom or both, then the signal is definitely digitally clipped. If it does not hit the edges, it's not digitally clipped. Analog clipping can be more difficult to recognize because what you're looking for in this case is a section of a waveform envelope that's flat rather than smooth or randomly varying. Periods of flat waveform envelopes almost never occur in natural undistorted recordings. You may have to zoom in on a segment of a call or sound to see if the waveform really is flattened out and hitting some maximum or minimum value either at the top or the bottom. And although clipping gives rise to extra or stronger harmonics in the spectrogram, it's usually not possible to distinguish these from real harmonics that occurred naturally in the sounds that you've recorded based only on the spectrograms. So you really have to look at the waveform to be sure whether or not your sounds are clipped. In many kinds of bioacoustic work, the spectrogram is more informative than the waveform, so you may be tempted to ignore or hide the waveform. However, it's a good idea to get into the habit, when you open a new file, to always look at the waveform, just to be sure whether or not the recordings are clipped. Okay, so what can you do with clipped recordings? Are there things that you can and cannot do? First of all, it's important to understand that clipping cannot be fixed or undone. Some digital audio editing software will include tools or effects that claim to fix clipping. These tools are really designed to restore short intervals in sounds that are audibly distorted in such a way that they don't sound distorted. And so they can make a recording sound better. But these tools really can't be trusted to perfectly reconstruct a correct, unclipped waveform for purposes of scientific measurement. If your purpose in working with the recordings is to make detailed measurements or description of the structure of the sounds, you should avoid using these fixed clipping tools in various audio editing programs. And as we've seen, clipping corrupts the spectral structure of a sound by introducing additional harmonic components in the spectrum that weren't really there in the sound that was received by the microphone. That means that frequency-based measurements from spectrograms, for example, peak frequency, center frequency, bandwidth, and so on, are unreliable if the signal is clipped. With clipped recordings, you really should not be using those measurements at all. Time-based measurements, on the other hand, such as duration, are unaffected by clipping. Finally, if your purpose in working with your recordings is only to identify or count sounds, it may not matter at all that your recordings are clipped, as long as you can recognize the sounds that you're looking for. So, how can you avoid clipping? If you're working with a portable field recorder, the kind you'd carry around for recording individual animals, such recorders typically have a peak LED that flashes on their display panel when clipping occurs. You should learn how to use the recording level meter of your recorder and that peak LED to adjust the recording gain properly to avoid clipping. And if you're using a directional microphone like a shotgun mic or a parabola, you can reduce the likelihood of clipping by carefully choosing your recording position relative to the animal you're recording and other sources of noise or background sound. So, for example, if there's a noisy road nearby, you want to position yourself so that the road is not directly behind the animal you're trying to record, because that will add noise to your recordings and in some cases could increase the risk of clipping. If you're working with an autonomous programmable recorder that you deploy in the field and then leave to record unattended, it's always a good idea to examine a short test recording from your actual deployment site and adjust the recording gain on the device. And if you possibly can, you should try to avoid deploying your recorder close to high-intensity noise sources like machinery or roadways or very loud moving water. That wraps up our discussion of clipping. Check out our next video to learn about another kind of distortion in digital recordings called aliasing. Thanks for watching.